Today was class 11. Last class we have discussed about how to find the pH of weak acid, weak base, and we have derived the relations of pH in terms of Ka and Kb. Today we are here to discuss some problems related to the pH of weak acid. See the question: calculate the pH of 0.02 molar acetic acid which dissociates 1% at equilibrium. So see the solution. Question number 1. The concentration of acetic acid is given. C equals to 0.02 mole per liter. This is the concentration of acetic acid given here, and alpha equals to 1%, that is dissociation. Degree of dissociation is 1%, and this means the value of alpha is 0.01. The value of alpha is 0.01. We know that acetic acid CH3COOH dissociates to form acetate ion CH3COO minus and hydrogen ion H plus and at equilibrium. In the last class we have also seen it is C mole per liter initial, and at equilibrium C minus C alpha. This is also C alpha. This is also C alpha. Therefore, hydrogen ion concentration of acetic acid at equilibrium is C alpha. Therefore, you can write that hydrogen ion concentration equals to C alpha. You can put the value of C equals to 0.02 into alpha equals to 0.01. This is equal to 2 into 10 to the power minus 4. So see, hydrogen ion concentration at equilibrium C alpha, hydrogen ion concentration at equilibrium is 2 into 10 to the power minus 4. Now pH equals to negative logarithm of hydrogen ion concentration, negative logarithm of hydrogen ion concentration minus log of 2 into 10 to the power minus 4. This is equal to minus log 2 minus log 10 to the power minus 4. So if you calculate it, this is plus 4 minus log 2 is 0.301. This is equal to 3.699. This is the pH of acetic acid. As I have told you in our last class that acetic acid is a weak acid. Therefore, from its concentration, given concentration, you cannot find out the pH unless the degree of dissociation is given, because this does not dissociate fully in aqueous medium. Its dissociation depends upon its degree of dissociation. What extent of dissociation will take place, that depend upon its value of alpha at a particular temperature. So this is question number 1. Now see, another question is calculate the pH of 0.1 molar hydrocyanic acid whose Ka is given. So Ka is acid dissociation constant. In the last class you have seen that Ka equals to C alpha square. So you see your last class, there you have seen that Ka equals to C alpha square for monobasic weak acid. K is given, you can find out alpha from here. So 4 into 10 to the power minus 5, the value of Ka equals to C is 0.1 into alpha square. Therefore, alpha square equals to 4 into 10 to the power minus 4. Alpha equals to 2 into 10 to the power minus 2. So you can find out the alpha up After that you can find out the hydrogen ion concentration and you can find out pH. So as I discussed in the previous problem, hydrogen ion concentration equals to C alpha at equilibrium. So C alpha, that means C is given, alpha is known, 0.1 into 2 into 10 to the power minus 2 C alpha. So this is equal to 2 into 10 to the power minus 3. So from this you can also find out pH. Another way, as I have discussed in the last class, that if you apply the formula pH equals to half of pKa minus log C, you can also apply, this is one method to find pH, this is another method to find pH. So pH equals to half of pKa minus log of Ka minus log C. So this is equal to half of minus log Ka. Is given in the question itself. K equals to 4 into 10 to the power minus 5. So this is double bracket minus log C. What is the value of C? C is 0.1, 10 to the power minus 1. So you can calculate it in this way. Half, this is equal to what? Minus 5 minus log 4. 5 minus log 4 plus 1. 5 minus log 4 plus 1. Minus log 4 minus of log 10 to the power minus 5. Minus of log 10 to the power minus 5 equals to 5. Minus log 4 minus minus plus 1. So 6, this is equal to half of 6 minus log 4. Log 4 equals to 2 log 2. Log 4 equals to 2 log 2. This is equal to 2 into 0.301. So this is equal to 0.602. Now this is equal to half into 6 minus 0.602 equals to 5.893. So this is equal to 2.699. This is the pH. So you can apply the second method to find out the pH, or you can apply the first method to find the pH. If you apply this method, then pH equals to minus log of hydrogen ion concentration. That means minus log of 2 into this. See here, I am showing it in the first method. This is first method. pH equals to minus log of hydrogen ion concentration. Hydrogen ion concentration 2 into 10 to the power minus 3. This is equal to log 3 log 10 minus log 2. This is equal to 3 minus 0.301. This is equal to 2.699. Same answer will be coming. So in this way you can solve. Some problems are there in your book, NCERT book. You will try to follow those problems. Now we are going to the next topic, that is common ion effect. Common ion effect. So common ion effect, here you see, say Newton common ion effect. So see, common ion effect, what is it? Let us take an example to understand it, then we shall discuss about the definition of common ion effect. Suppose you have a weak electrolyte H2S, hydrogen sulfide. It's a weak electrolyte. It dissociates in aqueous medium to form hydrogen ion and hydrogen sulfide ion, HS-. So this is a weak electrolyte. Practically hydrogen sulfide is a gas, you know. When it dissolves in water, it furnishes hydrogen ion, and so the nature of hydrogen sulfide is acidic. Hydrogen sulfide is acidic gas, and hydrogen sulfide are negative ion. This is the conjugate base. of the acid H2S. So it's a very, very weak electrolyte. in aqueous medium, you are adding hydrochloric acid to it, then it forms H plus MCl minus, aqueous H plus MCl minus aqueous. You are adding HCl. If you add hydrogen chloride HCl acid to the dissociation of hydrogen sulfide, then you can observe that hydrogen ion, this ion is common. This ion is common. Hydrogen ion is common. Clear? In this case, common ion effect will take place. And what is common ion effect? Common ion effect, you know that whenever you add a strong electrolyte having an ion common to the weak electrolyte, then the dissociation of the weak electrolyte is shifted in the backward direction. It is explained on the basis of Lee-Chatelier's principle. As you know, in the Lee-Chatelier's principle, if the concentration of any of the product is increased, the dissociation or the process is shifted to the backward direction. It is already discussed. So if you increase the concentration of H plus, it is one of the product, not it is product, but it is the species at the right hand side. Therefore, as the concentration of H plus increases, the process is shifted to the backward direction. So shifting of backward direction means what? The ionization of H2S will be reduced. This is the effect of common ion. Try to understand it. And how can it be defined? Defined in this way that the suppression of ionization of a weak electrolyte. I repeat, the suppression of ionization of a weak electrolyte, in presence of a strong electrolyte, having an ion common to it is known as common ion effect. So, what is the definition? The definition is suppression of ionization of the weak electrolyte. In presence of common ion, the ionization will be suppressed. That means the process will be shifted to the backward direction. Shifting of the process to the backward direction means what? Reduction of ionization. Suppression of ionization. So suppression of ionization of a weak electrolyte in presence of a strong electrolyte having an ion common to it is known as common ion effect. Now let us see, you have understood what is common ion effect. Common ion effect is very important in chemistry, and see, because of common ion effect, the strength of acid decreases, the concentration of the ions decreases, as in this case, the H2S, when it is in aqueous medium, there is a particular concentration of HS minus. But whenever you add acid to it, HCl to it, the concentration of hydrogen sulfide ion will be reduced. Concentration of the hydrogen sulfide ion will be reduced. Clear? See, same effect is very important in case of precipitation reaction. That will be discussed in your laboratory classes when you will carry out analytical experiments in class 12. You will understand the common ion effect and this application of common ion effect. Now let us take an example to see the common ion effect. Calculate the pH. Of 0.05 molar acetic acid, CH3COOH. 0.05 molar acetic acid in presence of 0.05 molar sodium acetate. Ka for acetic acid. This is what is K? K is acid dissociation constant. The acid dissociation constant, this is the weak acid. Therefore, its dissociation constant is K. K for acetic acid is 2 into 10 to the power minus 5. It is Dn. See how to deal with it. you see that how to solve this question. Remember here, acetic acid concentration of acetic acid is 0.05 molar concentration. Okay, in water it is taken, then it will be ionized into acetate ion and hydrogen ion. In this case, the hydrogen ion concentration will be more. But when you will take this solution in presence of 0.05 molar sodium acetate, then acetate ion will be common. In acetic acid there is acetate ion, in sodium acetate there is acetate ion. The acetate ion will be common. So the ionization of acetic acid will be reduced and the pH will be affected accordingly. Now see how to solve this problem. This problem can be solved in this way, that write down the dissociation of acetic acid, CH3COOH, aqueous, dissociates at CH3COO minus, aqueous plus H plus. So this one is acetate ion. Acetate ion can be also represented by Ac minus. Its concentration is 0.05 molar. Initially we have taken. Now the dissociation of sodium acetate NaAC dissociates in this way, aqueous dissociates in this way, Ac minus plus Na plus. So see, this is Ac minus aqueous plus Na plus aqueous. So this Ac minus ion is gone. This is Ac minus acetate ion, this is Ac minus acetate ion. And the concentration of acetate ion is sodium acetate is 0.05 molar. Taken. So whenever you take this concentration of sodium acetate in water, the entire part will be dissociated to form 0.05 molar acetate ion, 0.05 molar sodium ion, and this will be equal to 0. Because this is a strong electrolyte. Strong electrolyte fully dissociates. Therefore, the concentration of strong electrolyte given in water, concentration of strong electrolyte in water will be 0 after dissociation, because it will be fully dissociated. So what is the concentration of acetate ion? 0.05 molar concentration of acetate ion. Now this is the equilibrium stage. See, it has initially we have taken 0.05 molar. Let us consider the concentration of acetic acid that will dissociate its X. The concentration of acetic acid in presence of sodium acetate will dissociate X part of the concentration will dissociate. If X part of the concentration, X part of this concentration dissociate, it will be X, it will also be X. So what is the hydrogen ion concentration? Hydrogen ion concentration is X. What is the acetate ion concentration? Acetate ion concentration is X. What is the sodium? What is the acetic acid concentration? 0.05 minus X. Now the question is that this acetate ion is also present in the solution. What is the concentration of acetate ion that is coming from the strong electrolyte? 0.05. So add in 0.05, because the concentration of acetate ion is not X plus 0.05. In presence of 0.05 molar acetate ion, what part of acetic acid is dissociated? X part is dissociated. This X part is dissociated, therefore X part of acetate ion will form, X part of hydrogen ion will form. And acetate ion already present in the system is 0.05. Remember. Therefore, if you write Ka dissociation constant of this acid, it is acetate ion concentration multiplied by hydrogen ion concentration divided by acetic acid concentration. So see it here, acetic acid concentration. This is the expression of K. K equals to concentration of this into concentration of this by concentration of this. Now put their values. Ka is known. These values you put here. What are the values of acetic ion? X plus 0.05 into what is the value of H plus? H plus is X divided by what is the concentration of acetic 0.05 minus x. 0.05 minus x. This is equal to Ka. Ka equals to 2 into 10 to the power minus 5. Remember, the acid dissociation constant, this is an equilibrium constant. Its value will not change. Its value will remain same. Whether acetic acid is taken in water or whether acetic acid is taken in sodium acetate solution. Remember it. This is the significance of Lee-Chatelier's principle. If you increase the concentration of any one of the species on the right hand side, the process will be shifted accordingly in the backward direction so that the value of equilibrium constant remains constant at a particular temperature. So that's why it is happening, because Ka value does not change until we change the temperature. Therefore, Ka value will remain same. Ka value will remain same. Now see, this one is the expression. Now you have to find x in comparison to 0.05. The value of x is very, very small in comparison to 0.05. See here, because its Ka value of acetic acid is 10 to the power minus 5 order. So x is very, very less than 0.05. Therefore, neglecting x from here and neglecting x from here, we are getting x equal to 2 into 10 to the power minus 5. See here. How it is coming? This is neglected, this is neglected. Therefore, 0.05 by 0.05 cancel. What is left? X equal to 2 into 10 to the power minus 5. So, what is x? X is hydrogen ion concentration. Therefore, hydrogen ion concentration equals to 2 into 10 to the power minus 5. Therefore, pH equals to 5 minus log 2. 5 minus log 2 is equal to 5 minus 0.301. This is equal to 4.699. This is the answer. pH. So, in presence of sodium acetate solution, the pH of acetic acid will be 4.699. But if you don't take sodium acetate solution, you will find the pH. This is the concentration. This is the K. You will find the pH different. pH different. The pH will be lesser than this. pH will be lesser than this because hydrogen concentration will be more. If this is not present, this is not present, then hydrogen concentration will be more. If it is only taken in aqueous medium, this concentration will be more, so pH value will be less. So see, you can find the pH in aqueous medium only, and you can find the pH in presence of sodium acetate, and then you can compare the effect of pH after addition of sodium acetate to acetic acid. So these things are to be understood. So only by doing the problems, what is actually happening in the system, these things must be understood. So boys, you will try to understand the things. What is the effect? What is happening in presence of strong electrolyte? What is happening in presence of strong electrolyte? pH is changing, hydrogen ion concentration is changing, dissociation is suppressed. All these things are happening together. So you will understand it. Okay, boys. Thank you. Next class we shall discuss about the forward part of this chapter.